Okay. Good evening. Yeah, it's evening here. So I'll just do a quick video because my battery is really low. So I'll just try and as much fast as I can. Okay. I recorded the video initially, but the audio was having some issues. I don't know. I hope this one is good. Okay. So I'll start with the. Okay. I said I was going to show you how I joined the convolutional layers and the fully connected layers. So this is the class, the general class. If you, I said to you, I think initially when we started chatting, I said my neural network. That was the ANN. So this was just like an extension of it. I just added the convolutional layers and all the parameters to this one. So it's pretty much the same thing with that one, but this is just convolutional layers. So this is a neural device. So this is like the neural network, independent neural network. Every other thing is a parameter to train or set something or a function, just like backpropagation anything. But this is the neural network. This is the data structure for the neural network we have. So okay, no, I said I was going to start with convolutional layers. So first I'll start with that. Okay, it's the same thing. So this is a neural device. This represents one independent neural network. Yeah. So let's look at its structure. So it's a struct has a bunch of data structures in it. So now this is it. So when I said the convolutional neural network is just an overlay. Yeah, actually, just an overlay of convolutional layer on a fully connected, right? This is what I meant. So this represents our fully connected layer, right? And all of this stuff. Most of them are still the same thing in our fully connected layer. The only thing that's different is just this guy. This is our convolutional layer. So we just have to have a data structure to hold our convolutional layer, and then we have functions to connect the fully connected layer and the convolutional layer. So I think the main thing that connects both of them makes them have that's the main similarity between both of them is just the flattened layer, right? At the end of the convolutional layer, you have a flattened layer, right? And at the start of the fully connected layer, that's the input. So that input is the same thing as the flattened layer of the convolutional layers. Like after you do your convolution, you just flatten everything. So that's the input to your fully connected layer. So it's just that. Aside from that, you don't really have to even edit your ANN at all. You just have to work on the CNN independently and just connect both of them. And you have to connect above back propagation, because remember in ANN, we don't actually have to calculate the error of the input neurons because like the input layer. But in this case, we have to calculate the error because that error is going to be propagated back to the convolutional layers and used to uh, update the kernels and bias. Yeah. So the kernels are still the same thing. That you kind of treat them like weights, right? Just see them as weights, but in matrix format, like 2D matrix. Like I don't know if that's correct to say like that. But like just two dimensions, they have a row and column, like just like 2D image. I think if you watch commercial AI videos, you see they'll show feature maps just like 2 dimensions. Same thing as the filters as well. They're also 2 dimensional, and they're usually small, like 2 by 2, 3 by 3 or so. So those are the weights of the convolutional layer, as well the bias as well. So this is the convolutional layer, and I'm just going to check. Let's just see what we have inside of it. We have just some data structure. This represents the inputs to the convolutional layer. So what this means is that every convolutional layer is going to be built with this structure. So we might have two, three, four, as many as you want. This is an example of a code I was working on. This is M is actually I was training it. This is an example. We have only one convolutional layer here, only one. We can decide to add multiple ones, and it's just going to be us. We'll just be replicating this structure, creating a new instance of it. So this is padding. This just represents the padding we're going to do on the inputs of the layer. And then these are filters, which is the main thing actually. The filters like the main trainable parameter in the convolutional layer. We also have bias as well. We have pooling layers, and we have the outputs. Yeah. So this is like this also has a structure on its own. But let's look at the filters. So the filters, you see the filters like parcels, right? These parcels are uh, the number of kernels you have in each parcel is going to be equal to the number of channels you have in your inputs, the input image, right? And the feature maps amounts to the number of parcels we have. So we have kernels in parcels, right? And then we have multiple parcels, which is going to be the same number as it's going to be the number of feature maps we want to generate for that particular convolutional layer. I hope that makes sense. But if it doesn't, you're not really going to CNN now, so you don't really need that information. So I'll just go to the parallel processor. So I just want to lay emphasis that on the way everything is built. So this represents an independent neural network. So it means that if I spawn another instance of this, I have a new neural network, right? Which can run on a separate thread. That's just what it means. You just have to make sure your neural network is independent, right? Just create a mini structure which holds all the variables, everything. But this is going to be specific to that network. So now the only issue with parallel processing is it's very good, yeah. But the only issue that's where the drawback is the space, memory consumption. Right? So when you're training, you have to account for memories because imagine you have a GPU that has 1,000 threads. You have to spawn 1,000 neural networks. With each of them are going to have their own weights. Everything is just going to be duplicated for each of them. So just to like the way it works is like we have a central model. So just to like a converged model, we have a converged model. That model is going to be diverged. So it's like we now create multiple copies of it. We expand it and get multiple copies. So these copies are going to be trained independently on their separate threads. So this represents a particular copy with the input layer. It has its own input layer, has a clean layer, has the weight matrix, has everything. It even has its own batch size count. So just to in case of after a batch size, we can just account for that within that particular network or model. It has its own bias and every other thing. Has everything. Yeah. So it doesn't need any external data structure. It doesn't need to interact with any external data structure. Everything happens within this particular class. You can call multiple instances. You can save this in the vector, right? Just the same way we're doing here. So that's what we're doing here. So we save this present parallel net. So we're saving everything in a vector. So if I spawn 10 instances of it, all of them going to save in this vector here. And then, yeah, you can run independently. And let me show you the program where we actually initialize them. Parallel feed, yeah. So this is the function. Okay, yeah. So this is the point whereby we actually spawn the threads. So we create, like this is like the total number of neural device on this spawn. Not the total number of threads I wanted to spawn. Yes, my words. Okay, this is the total number of threads we want to spawn, and instead of then just create a for loop and then instantiate each thread. So this is the function which each of the threads is going to run. So this is a function. This function actually has both our feed forward, convolutional feed forward. This is the feed forward for the fully connected layer. Then it has get output error. Then it has backpropagation. So just as this function, all of them are going to do that independently. And also, if you check here, sorry, no, sorry, sure they are correct. Let me use the control F. I'll just search this stuff again. Okay, yeah, okay, this is where we were. So if you check here now, you see we're actually creating subsets. So what we do before this represents a single epoch. This operation run every epoch, right? So what before the epoch actually starts, or when it starts actually, we just divide our data set into a range. So what we're not actually dividing it into like we're just getting its index, right? Just get all the index. So that's gonna help us save memory instead of us duplicating and dividing and doing all those rubbish operation that's going to consume memory space for during training. We just get the index, just the index number, just integers, store it in vector, then we can split them and then assign them so that just assign the vectors to each of the threads so they know exactly what index of data set, data sample they're going to access. So that's going to reduce memory consumption, I guess. Whoa, actually slow. But anyhow, that's I think that's much of it. That's all. So you just make sure your threads are independent. Just the main functions, the core functions that you want that the neuron actually depends on. Every other thing is a setting. The functions are settings, right? You just make those ones global functions that any of them can access, right? And that makes sense. Just make them global functions so that they just like call the function and just pass. So, but just anything that you want them to hold personally, it should just be in a that they can actually just work with localized. They don't have to interact with anything outside. That's the whole concept of parallel processing. And you just have to be really careful because it gets complicated. It can get really complicated. Yeah. And I'm actually having some challenges with this one neural network. It's not actually I was trying to train MNIST, but I'm not really getting a high accuracy. I did a test some time ago. I think day before yesterday. I did a test. Let me check. So I did a test, and of course, this is not actually true. I was using a wrong accuracy formula. The actual accuracy for this is probably like 88% or 89. So it's not actually that high. It's not as high as 97. I was using the wrong accuracy formula. But this actually still performs somehow well. So I'll just show you an example. This is one I've already trained. So I trained three models. These are their alleged accuracy. These are false accuracy. But they're still good somehow. They still perform well. So these are the accuracy, and I just train them so I can just like see at least get something working. So the first, I created a way to visualize the MNIST dataset because I downloaded the CSV version. Let me just open the main program, like the main dataset. Uh, okay, my battery is going low. Let me just try and do fast before battery dies. Uh, Here, yes, yeah. So it's actually in CSV. It's just like bunch of pixel values. Once it opens. Okay. So it's a bunch of pixel values, a lot of pixel values, just like numbers. So you can just grab any random set. Just grab any random one. We're going to try to predict what it has. Okay, just grab this random guy. Copy that. Just copy all the pixel values. These are labels. Just copy that, and then I'll go to let me see. Yeah. So go here. We'll just control copy everything here. Paste this here. So I'm going to run my make mlist underscore c. So this is a function I wrote, so I can actually see, how it looks like. What is it that I can train? Can then test my neural network to see what it looks like. So this looks like an 8. But this is a very bad way to write it. But let's test and see if the models are going to recognize it. So I just run this. Yeah, correct. So they all predicted as 8, which is good. So they're not actually all that bad, but they work. They're not just like they're not that accurate, but they still work. Sure. So that's it. I think that should wrap up this video. Yep. Yeah. So I'll just close it and see if I can upload it before the battery dies. Yeah. So in case any other question, you can send a message. Stop.